Good morning, everyone. Welcome to class. So, today we are continuing with a section of dimensioning called tolerances. I trust you have found the lecture slides on ClickUp. Okay, so let's jump into it. We've got quite a bit of stuff to cover for today. So, tolerances. A tolerance is basically like a detailed dimension. So it doesn't just specify the size, it specifies a very accurate value for the size and usually gives a range of values which are deemed acceptable for a size. So a surface tolerance, that's the first one we're going to look at, is a measure of the roughness or degree of finish a surface must adhere to during the manufacturing process. On slide 2, a surface tolerance is a measure of the roughness or degree of finish a surface must adhere to. Then we get limits and fits, which basically specify the allowable variation on a dimension or a surface of a machined part. And we'll end the lecture with geometrical tolerances, which basically control the shape and positional distribution of a component. So, surface tolerance, also known as surface texture, is indicated by a symbol that almost looks like a check mark. The open check mark indicates the surface finish obtained by the non-removal of material, meaning this one specifies how rough a surface may be, but you're not allowed to cut or grind or polish it to that roughness. You have to use a different process like an electroplating process. The one with the closed triangle, the removal of material, for example, milling, turning, drilling, and so on. This symbol is known as your machining symbol. And then we get the one with the little circle in there, and this indicates a surface finish where the material removal is prohibited. So it's associated with a primary manufacturing technique like casting, which you did in the manufacturing classes, forging, rolling, and so on. You don't really have to know exactly what these are at this stage. Good. So, the surface tolerance. At the surface of a material, you might have an altered layer. Remember in the previous slide, we said like an electroplating process, or it could be a chemical process on the surface. So you could have an altered layer, and this is now super zoomed in. And there you can see the roughness of the surface. And substrate is basically just the bulk of the material underneath the surface. So if we zoom out a little bit, then a typical material surface could look something like that. And there we have, if we zoom back in again, we have a roughness height. And that roughness height is basically your surface finish. It's a measure of how smooth the surface is of the material. Okay, so this is our machining symbol, and we can actually show quite a few things on this machine symbol. The main one that we are going to use in MGC is the surface texture. So note that surface texture, also the roughness height from the previous slide, this value is given in micrometers. So if I have a 3 or 3.2 or whatever on top there, that shows that that roughness height is 3.2 micrometers. So it's a very, very small. Now I just want to quickly show you okay, that's still working. Good. So What I have here are a couple of different random objects. This one over here is my little LED torch, and this surface has been altered by means of an electrical process. I won't really call it electroplating, it's an electrical oxidization process called anodizing. So if I just quickly unscrew this tail cap, you'll see on the inside there it is silver. That is the raw aluminium. And then the black on top of that is the electroplating or electrical process to change the surface of the material. So this surface will then be indicated by that first machine symbol, just the open one, that you will use to indicate the roughness of this kind of surface. You can now imagine you wouldn't necessarily want this surface to be mirror smooth, but also not too rough. So if it's too smooth, then it's going to start to slide out of your hands and not give the nice matte finish that it has over here. Okay, so this surface finish was obtained with an electroplating kind of process, although it's not specifically a plating process, it's an oxidization process. This is a magnifying glass, basically. And you'll notice on the inside of the magnifying glass, there on the inside, let me just get that right, there on the inside where my finger is, you'll see it looks like a mirror on the inside. Obviously my finger isn't really shaped that way. So it looks like a mirror on the inside. That's due to the purpose of this device. This is a zoom lens that I built for an LED torch of mine. So on the front it's got a magnifying glass, and on the inside there I polished the internal surface to a mirror-like finish. There from the side you can see it better as well. So that's the smoothness of the surface. So that surface on the inside there has to have a very, very fine surface finish to be able to actually act like a mirror. The outside of this body didn't need it to be that smooth. So you can actually, if I bring it close to the microphone and scratch it, I'm hoping that you can hear that. That sound is the sound of my nail scratching over the surface. So the surface is not a completely smooth surface, mainly because it doesn't need to be. Okay, so this little, well, not so little, but this zoom reflector of mine is able to double the beam intensity of my LED torch to make it shine further. Okay, let's go back to the lecture slides. So that surface finish or surface texture over there, the inside of my zoom reflector would have quite a low number over there, probably a fraction of a number, not a whole number, where the outside over there will have probably something like a 20 or so. The other values, yeah, it's important for you to know what goes where, but we're not specifically going to use them. Okay, so you can place these machine symbols. That letter A over there is just to show where the numerical value for the surface texture would be. So if it was my zoom lens, then obviously on the inside there, it would have a low number, and this one on the outside surface would have a higher number. Information is read from left to right or bottom to top, same as we do with the dimensions. They can be placed on a surface or on an extension line referring to a surface. Just for interest, some surface tolerance values obtained by various manufacturing processes. So turning, that's the process I used to make the outside of this reflector. You can typically get values between 20 all the way down into fractions of micrometers. But this now becomes super, super fine turning. Something that you would typically do with a diamond tip cutter instead of a normal cutter. So mine probably lies here between the 12 and the 6 somewhere. Polishing, however, that's what I used on the inside of the reflector, can go way down into small fractions of a micrometer. So here you're talking 50 nanometer variation or roughness on the surface. If you want to specify to have a component made like this reflector of mine, obviously the surface on the is enough to be able to do its job. So when making a drawing of this component, you would want to show the person who has to manufacture it how smooth the inside surface must be. And for that, you will use your surface finish symbol. And then you could use that little symbol with, for polishing, let's say a 0.05 there where the A is. So that shows the person making this component that he has to now do additional processes on the inside surface to make sure that that thing's smoothness is smooth enough to be able to do its job. Another place where these symbols would be very important with a very low number would actually be on the magnifying glass itself. Obviously, it has to be as smooth as possible so that it can gather the light and focus it correctly. Okay, so limits and fits. All manufactured parts are subject to manufacturing tolerances. No two objects can be exactly the same. So you might have a shaft that you think has a diameter of 10. If you measure it very accurately, might be slightly less or slightly more than that. And this difference in actual size may be described by a tolerance. So you as the designer might specify that it is allowed to be between 9.9 and 10.1 for your specific purpose. But one has to look at these small decimals because you might be tempted to think that 10.03 is close enough to 10, but you might get a problem when a 10.03 shaft needs to fit into a hole that is 10.00, which will have a bit of an interference between them. And that is why these tolerances on the dimensions are important in manufacturing. So yes, these are for manufacturing purposes that we put those there. And sometimes we need to specify the tightness between components, and we do that by means of a tolerance. At the front of this reflector of mine, this shiny ring that holds the optical element in place is actually pressed over the rest of the body. So I specified that this ring must be slightly smaller than the outside of the body so that I have to physically squeeze them together, and then the friction will cause everything to stay in one place so it doesn't rattle when you shake it. Okay, now something interesting. Consider these brass pipes of mine. Brass is just a mixture of copper and zinc. If I measure the diameter here at the top, so that one is 11.447 millimeters. If I turn it 90 degrees, there it's 11.537. So this thing isn't perfectly round. Let's see the next one. 11.454. 11.425. Okay, so I'm assuming that you can see that my point is these aren't all exactly the same. This one is 11.393. by 11.447, and so on. So you can now see I have these 4 little pipes, and they were actually sized by a very specific sizing process to try and get them exactly the same diameter. And in these 4 examples, not one of them read the same values as the others. And that is where the tolerances are important. So for this pipe, I can actually specify what would be acceptable values for this pipe to be able to function in the application where I want to use it. Okay, so you now saw that those 4 pipes of mine had different diameters, and it is actually quite acceptable for them to differ because it's physically impossible to make them exactly the same. So what we can do is we can specify a minimum and a maximum size. We measured on the outside, so let's use the shaft example. So it might have a maximum diameter and a minimum diameter, and the difference between those two are specified by a tolerance. This is drawn exaggerated just so that you can see it, but you saw on my measurements the variation was typically about 50 micrometers. So we have different fit categories. The first one is a clearance fit. So that basically says the variation in the holes will be such that even the smallest hole will be bigger than the biggest possible shaft. So that's a clearance fit, meaning no rattling, but loose enough to move easily. So it's not so loose that it will just fall out, but it can slide the one in the other one. The second type is a transition fit, where some of the shafts would be bigger than some of the holes. And interference fit is basically when all of the holes possible, or all of the allowable variation in hole diameter is smaller than all of the variation in outside diameter of the shaft, which feels impossible. But interference fits rely on material elasticity. So the outside component stretches and the inside one compresses to yield a very tight connection with high friction to resist any movement. Okay, so there is a standardized way to actually, it is done with this weird designation. So basically the number in front is your base or zero line dimension. For example, the 10 millimeters in our 10 millimeter example. Then this inside of the brackets is my tolerance. So the tolerance now specifies allowable variation for the hole, and it specifies allowable variation for the shaft, and these letters actually specify the fit category. So we had clearance fit, transition fit, interference fit. So that's actually specified by this value over here. Again, this kind of information would be specified by the designer of the part. So in my reflector example, I knew I wanted a certain amount of tightness between the two, and that then allowed me to choose a certain fit grouping or type that allowed the tightness that I actually wanted it to have. The capital letter H refers to the hole, and the numerical value refers to the width of the tolerance band. The G is for the shaft. It's not always a G, it can be an N or whatever. And then the number is also for the band. Let me show you the table that these come from. So at the top of this table, you'll notice a H, and so capital H, small letter next to it. both have numbers to them. So the H7G6 is this fit column over here, and it falls under a clearance fit, meaning all of the holes will be bigger than all of the shafts. For my reflector ring example, I was probably somewhere in either this category or up to there somewhere. I didn't specifically choose a value, I just measured it until it was tight enough and then I forced it on there. Okay, so also remember you have to use the H and the G that are next to each other. I can't use that H with this G. So it's one band that I'm using, H7G6 or H7K6. So this is the way a tolerance is given, the zero line dimension and then the fit category. So an example says calculate the tolerances for a shaft and hole combination with the ISO fit standard 25H7G6 and show it on a drawing. So the first step is to determine the tolerance values for the given fit standard. First we look at the diameter, the 25. So on the left hand side we have the sizes from 0 to 3, bigger than 3 up to 6. So this is including that is bigger than 10 up to 18, bigger than 18 up to 30. So 25 lies between 18 and 30, meaning we must be somewhere in this row, shown with the red block. Then, the tolerance band that was specified was H7G6, so at the top we search for H7G6, so that gives us the column in which we can find our values. So you'll see at the H, at the hole, we have a 0 and a plus 21, and at the G, the shaft, we have a -7 and a -20. So basically, what that means is for the shaft, the G6, it shows -7 and -20. And these values are given in micrometers. So that means you take your 25 zero line dimension value and you subtract 7 times 10 to the -3 from there, because it's a micrometer, this is a millimeter. So that gives you 24.993. And then the other value said -20, so 25 minus 0.020 gives you 24.98. So that means a fit with a G6 on a zero line dimension of 25, it means the shaft, any shaft that comes from that production line must measure between 24.98 and 24.993. So it must be between those two values. For the hole, we can do the same. We add a 0 and a 21. Again, remember those values are in micrometers. So it's 25.000 plus 0 and plus 0.021, meaning the hole must be between 25.0 and 25.021. So now you can see any hole that comes from this process, the person manufacturing it must ensure that the hole lies between these two values. If it is outside of those values, then that part isn't made according to the drawing. So these are the values that we then obtained for the hole and for the shaft. Then you show it on a drawing. For the shaft, the bigger number is on top, because as you make a shaft, you start with a big diameter and you cut it smaller. So the first value you encounter is the bigger one, and then you encounter the smaller one. For a hole, you start small and cut it bigger. You can't cut a hole smaller. You cut it bigger, so the first value you write is the small one and then the big one on top of that. Okay, next one is geometrical tolerances. So these tolerances basically control the shape of a component. So for example, you can force something by the design to be a certain roundness. So for those little pipes of mine, I could specify that they must be round within a certain variation. Or if we go to the camera again, this pen must be straight within a certain variation. So you can measure the waviness of the surface, or we could even specify the allowable variation on the diameters through the length of this pen. So there we have a 14.96. There we have a 14.85. And there we have a 14.87. So one could specify exactly how cylindrical this pen needs to be. Obviously, this is a pen, so my hand won't notice a 0.1 millimeter variation in the length of this pen. But if this was a precision instrument, for example, that little shaft in there, then I could specify, or have to specify, a very, very tight value, otherwise that shaft won't function correctly. So basically, what today's lecture is about is when you have components manufactured, you must appreciate the fact that if you put a dimension on a component, then the person manufacturing that needs to know how close to that dimension must they be, because it's physically impossible to get onto a dimension 15.0000. So someone making something, manufacturing something, must be given a ballpark in which they can operate. So the diameter for the pen must be allowed to vary slightly, and the designer of the pen can actually specify the allowable variation. Okay, geometric tolerances, as I said, they control the shape of a component. Another example would be in your clutch pencil, the hole has to line up with the lead being fed through it. So you could specify how concentric the hole in the tip of your clutch pencil must be to the center line of the clutch pencil. Remember, you can't just specify everything to be perfect. Firstly, because it's almost impossible, and secondly, it's going to take a lot of time for someone to then measure each component afterwards to make sure that it is actually as perfect as you require it to be. So geometric tolerances, you have a single feature one, which controls things like the straightness of an edge. So a ruler would be an example of that. When you make rulers, your company manufactures rulers, then you can specify how straight the ruler must be. It doesn't have to be so straight that it has a 1 micrometer variation. You're going to use it to draw a line with your pen. So then up to a 0.1 millimeter variation would still be quite fine. Flatness, if you have something like a flat mirror, then it would have to be quite flat, otherwise it will distort the image. Then you can specify a smaller number for the flatness. Roundness is the example I showed with those little brass pipes of mine. Cylindricity was the example I showed with the pen. Profile of a line can be specified, or the profile of a surface can also be specified. Then you also get related feature geometric tolerances, where it basically just refers one feature to a different one. You can have lines that are parallel, you can specify an angle, specify perpendicularity, position, concentricity, like the clutch pencil tip example, and you can specify symmetry or wobbling of a shaft. So this is the way a geometric tolerance is indicated. You point to a surface, then you show the type of tolerance that you want it to be. This is a straightness tolerance. And in this case, the value is in millimeters again. So that is straightness within 0.1. You can do a related one. So you can say that this surface must be perpendicular within 0.1 millimeters with respect to reference A. And then you plonk a sticker on A that says there is A. So that one must be perpendicular within 0.1 millimeters of that one. You can just go and have a look at the different ways to indicate these on a drawing. So basically, let's quickly have a look. The straightness geometric tolerance says this surface, the one I'm pointing at, must be straight within 0.02 millimeters. So if I go from the highest to the lowest point on that surface, the variation must be less than 0.02 millimeters. Flatness is basically just straightness in two directions. So it shows that the highest and the lowest point must be between 0.02 millimeters from each other. Here we've got the roundness, the one that I showed you with those little brass pipes. So you can say that this surface must be round within 0.02 millimeters. So the variation in roundness must be less than 0.02. And so on. There are just a couple of examples. Perpendicularity is measured as a distance, even though it's actually an angle, and it's measured by the displacement of the perpendicular axis.